So moving on to the topic of cloud workloads and specifically containers. We now want to talk about the distributed container runtime, talking about the rapid provisioning and large-scale management of containers. Now, we position here Atomic Enterprise platform as the premier container runtime based on the open source standard Docker and Kubernetes, and it is actually based on the work done on Red Hat OpenShift version 3 as platform as a service that we will look at in the next use case. So really we'll be showing Red Hat OpenShift platform version 3, Red Hat OpenShift Enterprise version 3 in this scenario. And it really, what the main benefit is it allows us a highly efficient operation of large-scale container landscapes through declarative configurations for container-based applications. For example, things like high availability, things like failover and persistence are all declaratively configured. We just have to define what needs to be achieved, and the system figures out how to get there automatically. In the future, this container runtime will also be integrated and can be managed by the underlying management tool. So CloudForms, as you've seen it in the next major version, will be developed towards a management environment also for those container landscapes. And Red Hat Satellite, as it is now, is also enhanced to be a enterprise container repository. So from a use case point of view, let's assume that the various different steps required to actually roll out OpenShift and Atomic Enterprise platform have already been done. And I'm now using the environment to actually run a container. The format of the demo will change a little bit now. We probably will become a little bit more slide heavy, since I do want to ensure that container concepts are known, or that at least we have common basic understanding of containers. So containers package the applications with their dependencies and they isolate the runtime. That makes them very easy to deploy and very portable across different host systems. So really you have a container, you have the application and the required libraries, already as everything as part of that single container, and you can just move one container from one host operating system to the other host operating system and have the same configuration running there. The common piece is the actual operating system, including the kernel plus the core operating system runtime and the hardware. So the hardware needs to be compatible and the operating system needs to be compatible. It's not that you can take a Linux container and run it on a Windows environment. It needs to be a Linux environment. We're doing that through 3 isolation mechanisms. We're using C groups that are part of the Linux kernel to isolate runtime aspects like load and usage, so that no single container can allocate all the resources of the host operating systems. We're using kernel namespaces to give each one of those containers its own view on the system, so he has its own set of file system, network interfaces, etc., and he does not know anything about the other containers. And we're using SELinux, as word IP tables, etc., to create security barriers between the various different containers. So the main benefit of containers is that they provide a very high density and a very high efficiency. You can run hundreds of containers on a single host, where you can run probably only tens of virtual machines on a hypervisor on a host. However, that is done at the expense of isolation. So the drawback is that virtual machines, through the abstraction of a hypervisor, probably provide a greater isolation between each other than applications running in containers. However, the containers really provide great agility benefits. So whereas in a physical server, until it was instantiated and up and running, you probably took more than a day. For a virtual machine, you probably still need 10 minutes to quarter hour. With containers, we're really talking about instantiating a new container within tens of seconds. So what's the benefit of our container runtime now? Kubernetes really replaces the manual tasks that you have with declarative goals for containers. So if you look at a standard use case, you have a user and he wants to manipulate some data on some storage. And what would have to be traditionally set up is, well, you need to configure a relational database management system, probably in that own virtual machine, that is talked to by an application server, that is available through a load balancer so that the end user can actually talk to it. And then you have to ensure high availability. So you set up a second load balancer and need some sort of round robin DNS to ensure that either of them can be reached, or you need some sort of failover mechanism that needs to be set up. That is an actual administrative task that you need to do. You need to set up the application server and to configure it to properly be able to host the required application. That is a manual task that needs to be done. You need to configure the various different resources that are available in the application server, like the database connection. That is a task that needs to be done. You need to configure which storage the database system will use. You need to allocate that storage. That it's a task that needs to be done. You need to set up a high availability concept for that relational database. That is, again, a task that needs to be done. And each one of those tasks is basically an administrator performing a sequence on steps of the system, and that is very high effort. There's a danger of the need to reinvent the wheel everywhere, because once you've set up one relational database system, the next one is probably very similar, however different enough that you just cannot simply copy over an RDBMS installation to a new system. So you need to reinvent how to set up a database, for example, again and again. And that's the reason why it's really hard to achieve consistent quality, because every task, when it's done again and again, it's done slightly differently. So it's hard to achieve consistency here. The main benefit of that task-based approach is that no matter how complex the setup is that you want to achieve, you can really do it. I want to contrast that with the declarative approach that we have. Declarative goals just say, I want high availability, I want persistency. So here we have, in a Kubernetes environment, we have the concept of a project, which is basically the namespace, the bracket across everything. And within that project, we have what we call pods. A pod is a combination of one or many containers that are scheduled to run on the same underlying host. And a pod is, again, a declarative goal. So you just say, I want this pod to consist of the following containers, and then that pod is instantiated that way. You have a concept of a replication controller, which is, again, a declarative goal. You just say, I want a replication controller that ensures that 3 of those pods are always running. Then you will have 3 of those pods running. And if one pod goes missing because the underlying host goes down, or it is deleted, or it runs into an error and terminates itself, the replication controller will ensure that, again, another pod is launched somewhere in the environment, and again, 3 pods are running. So really, you just declare goals that the system tries to achieve all the time. Now, there's an interesting concept, because the pods can run anywhere. How can we do communication? How can one pod reach another pod? How do the application server pods know about the RDBMS pod? And this is really the concept of a service. That is another declarative goal. So pretty much the service is a fixed IP address that is just there, and we know that all of those pods can be reached through that single IP address of that service. So the service encapsulates things like identification of it. So you can simply look it up, for example, through DNS. What is the name within a project? You have the name of a service. What is its IP address? That is just a DNS lookup within a pod, so that he finds, well, the service for the database is available, for example, through a specific IP address. What also happens is that the service is completely independent of any pods running. So there could even be 0 pods, the service would still be there. The IP address would still be a valid target for connections. So pretty much what the service does, it performs a load balancing of IP connection requests towards the pods that are there. Of course, if no pod is running at a certain moment, the connection will fail. However, if you have 3 pods, it will spray the load between those 3 different pods. If you have 5 pods, it will automatically send the connection requests to those 5 different pods. It doesn't really matter. So a service is really something that provides load balancing and addressability across the container landscape, no matter on which host the pod is actually running. So each service has an IP address, and that is valid within the project. If you want to actually be able to access a specific service from outside, so for example, let's assume the consumer wants to talk to the application server, that service IP address is only valid within the environment, within a tenant of OpenShift. However, we can specifically expose a service as a host name to the outside, and this is a route, another declarative item that configures that if a route is configured, pretty much what happens in the underlying system is that high available routers will be configured to then act as proxies from that specific host name to the specific service, which then sends those requests over to the various different pods. So that way, wiring, setting up the environment is very easy. We just define declarative goals and the whole setup will take place automatically. So let me give you an example of what this looks like. The first one is very simple. Let me open another tab. I'm not showing you the web UI right away. Let me show you the web UI right away. So this is the OpenShift web UI. And I'm logging in as root. And here I can see a number of projects that are already there. I have to admit I forgot to clean up, so let me do that right away. I will now log into the OpenShift master. And first I want to clean up. I'm using a command to and the other one I wanted to set up. Sorry for this. Okay. Now you can see, once we refresh, we only have a very limited amount of projects there already. So let's create a new project. So the OC is the OpenShift command line, and I'm now creating a new project which is called Java sample. New project, and the name is Java sample. What this does, it creates basically this empty namespace, this empty bracket across all the different resources that I mentioned before. And as you can see in the web UI, it turns up here. When I open it, it is really empty. There's nothing in there. So the next thing I want to do is I want to take an arbitrary Docker container and just run it. This arbitrary Docker container is, for example, Sonatype Nexus. So Nexus is an application that is available on Docker Hub. And all I need to do is I need to say OC, just a second, new app, Sonatype Nexus. And what happens now is that various different of those declarative goals are created. I have a deployment configuration, I have a Nexus service created. So let's look at what it looks like here. And you can see the Nexus container is already running. Pretty much what you see here is I have a service called Nexus that has an IP address 172.30.99.43. And within that, there is one specific deployment that has one pod running. So this specific pod is actually running the Nexus container. At the moment, I cannot access it from the outside. However, once I expose that service, once I create this additional declarative goal of a route, I can access it from the outside. So I say OC expose service Nexus, and this creates a new route. This is also reflected here now that there's an actual name behind it. And when I open it in a new tab, I can see Sonatype Nexus is actually running. So it is really easy to get an arbitrary Docker container that is already available in Docker Hub running in our OpenShift environment, in our Atomic Enterprise Platform environment. So now if I wanted to scale, for example, before we go into scaling, what has actually happened? So a number of those declarative goals have been created. So let's look, for example, at the OC get replication controllers, get RC, or we could even write replication controllers, but this is a very long thing. I can see there's a Nexus 1 replication controller. And I can even get a bit more details. I can ask it to describe this replication controller Nexus 1. And you can see, for example, that which Docker image is part of that pod, how many replicas are there, how many are desired, how many of those pods are running, etc. So there's a number of information that we can get at. And this is the type of goal that the system actually operates and converges again. So now if we say, okay, one single Nexus is not enough to actually handle our load, I could even scale it. So I could say OC scale the replication controller Nexus 1. For example, I could say replicas 3, like this. And what now happens is that the 3 pods are running, because basically the containers, the replication controller looks at the current state, sees only one container is running, 3 containers are supposed to be running. It immediately launches those additional pods, and since the containers start within seconds as opposed to minutes or hours, they're just simply there. And now whenever I would request this web page, pretty much I would be distributed via round robin among those running instances. So this gives you a very small indication of what it means to use declarative goals. I just say what I want, what I state I want to have, and the system really converges toward that desired state. I just say, run this container, run it X times, and the system ensured that this is running. Drawback of this declarative goal approach is that it's only applicable for the most common setup. So if you have really something exotic, it mightn't work, but it probably will work for 95% of all your requirements. This is just a summary. As you see, in a traditional way, you have a lot of manual tasks or even configuration management tools like Chef, Puppet, Ansible, or Salt helping you with that. With an infrastructure as a service, with a pure infrastructure as a service, you might have some APIs to do certain tasks, but it still requires and allows scripting. Some of those tasks also still might need manual task config management. And with our runtime, basically everything is just a declarative goal. Once you can say, I have everything in containers, you just say what you want, and the system will ensure that it actually happens. The infrastructure of that runtime itself is, again, cloud ready. So you have highly available masters that replicate the information amongst themselves. If one of those masters fails, the other continue to run and ensure that the state is still present. you have a number of nodes that actually run the various different containers. And here you have very intelligent mechanisms based on labels to select for each workload the proper node that that a specific container can run on. So you can ensure that a specific container only runs on nodes that have certain characteristics. You can ensure load balancing among your cluster landscape using that. So they're very, very sophisticated mechanisms of actually ensuring that all the nodes are utilized evenly and that you can add and remove nodes easily to your container cluster. The service layer, already mentioned, is a software-defined networking layer that ensures that any service is addressable with its own IP address. And if you want to be able to access the application from the outside, the routing layer will ensure that an externally visible name is actually associated with a service and can be reached externally. It can run on any environment. It runs really well on OpenStack, but it can also run on traditional virtual environments, on physical hardware, as well as public clouds. And very important is we have the concept of persistent storage as part of those declarative goals. So again, it's very easy to say, I do not only want to have stateless applications running in my container landscape, but I can also say a specific container wants to allocate a piece of persistent storage, and the system will ensure that this takes place, so we can have even stateful applications that persist their state into a storage environment running in our OpenShift environment. So the real benefit for IT ops is that we have a secure and enterprise-grade container-based application platform already available. It helps the operations guys to enable the application developers, on the one hand, to easily run container-based workloads at the same time as it improves the operational efficiency and ensures that there's a very high utilization of the underlying infrastructure. As I mentioned, there's these advanced scheduling mechanisms and automated placement mechanisms with regions and zones for high availability based on labeling schemes. But it's really very flexible due to that labeling scheme, so you can really do any type of environment there. I already talked about the declarative management goals, and it is also quite easy to integrate the whole environment with enterprise authentication systems, so you have that as a platform that not only is a standalone environment, but really integrates with what you have with regards to identity and access management. One thing I only want to cover very briefly is, even though I just showed that you can run an arbitrary container from Docker Hub, you should never blindly trust publicly available containers. So for example, if you just say, look for MongoDB on Docker Hub, you could see that there's a large number of available containers that provide MongoDB, and you do not know if you have just an arbitrary container, who built this image, what's its purpose, was it created for production or just for demo, can you actually consume it, who will maintain it, what happens if an errata is identified within a container, etc. So Red Hat proposes the concept of container certification. This means Red Hat will provide a set of containers that are trusted, that undergo rigorous testing, that go on an update mechanism by Red Hat, and it provides a container certification kit for ISVs to build their specific containers on, that allows them to then sign those containers, so that you know that it went and underwent a testing process, that it was based on a trustable image. And we suggest you to set up your environment that way, that only trusted containers can be deployed, that, for example, Satellite 6 could act as a repository for those trusted containers that then form the basis for additional deployments in Atomic Enterprise Platform or OpenShift Enterprise. So that concludes the core runtime demo. I just